So, Mr. Baldwin, you ready to talk a little bit about earthquakes?
Yeah, let's talk about some earthquakes today, Miss Awad.
Okay, so last time, on the last video, I think Mr. Ben and Mr. Z talked a little bit more about PNS waves, so everybody should have a really good understanding of what happens with PNS waves. So what are we going to do in this segment?
Well, today we're going to use our knowledge of PNS waves, and by the end you should be able to explain how PNS wave shadow zones are created at the surface of the Earth.
Okay, good.
So, some of the things that we already know.
Okay.
As you go deeper in Earth, what happens to the pressure?
Pressure is going to increase because you have more material piled up on top of you, right?
Absolutely.
Okay, so confining pressure, that's what we're talking about here, right? Increases with increasing depth in the Earth.
Absolutely.
And that's from the surface all the way down, right?
All the way down, straight to the core.
Okay, good.
And then with temperature, we talked about this with subduction zones. As it gets deeper and deeper and deeper, it gets hotter and hotter and hotter, right?
Okay.
Okay?
And we have a specific name for that. That's called the geothermal gradient.
Mm-hmm.
So we're saying that temperature also increases with increasing depth.
Mm-hmm.
All right? And that's what this picture is really showing us, right? So the arc up here would be the Earth's surface, and then going down towards Earth's center. So the depth increasing, and as depth increases, the temperature increases, and the pressure on the material increases.
So if you were to travel from the crust all the way to the core, it would get more and more pressure,
Yes?
and more, it would be hotter and hotter temperature.
Correct.
Okay, good.
So the velocity of the seismic waves we talked about in the last segment, they increase with depth, and that's because of the increase in density of the material, right?
And so as you get deeper, those waves are going to travel faster and faster.
Okay, and what that actually does, if we think about being able to actually look at the path a wave travels on, so if you could hop on that wave and ride along with it,
Oh, man.
that would be very cool.
Yo,
right?
way cool, yeah.
So that path actually is not straight, and it's not straight because the material that it's traveling through is constantly changing because the pressure and the temperature are constantly changing.
So you wouldn't go straight down because you would be speeding up as you went down, and you would start to curve around through it, right?
Exactly.
Okay, cool.
So the ray path is actually a curved path.
Okay.
Okay.
So we're going to be talking about reflection, refraction, a little bit of physics. Have we talked about this in physics,
we're
maybe?
going to try to understand the curves and the changes in direction of those seismic waves as they move through Earth's surface.
Okay. So something we already know, reflection, term you guys are all familiar with, change in direction of waves due to hitting a reflective surface. So like looking at a mirror would be like just changing the direction. Light bouncing off of a mirror, bouncing back to your eyes.
Okay. And a different term, which is the term refraction, is also a change in direction, but this time that wave is actually going to penetrate the boundary between the two substances.
Okay.
It's going to go through that boundary. And when it goes through, because the material on each side of the boundary is different, it's going to change the path it travels on. So its velocity is going to change because it's entering into a new material.
Okay.
So what are we seeing in this diagram? We're seeing a boundary between air and glass, and we're seeing an incident ray, or seismic energy if you want to think about it that way, coming down and reflecting or bouncing back off that boundary.
Just like if it was a mirror, the light bounces off the mirror.
Yeah.
Okay.
But because it's air and glass, we know that some of that light is going to actually penetrate and travel through. And when it does, it's going to take a slightly different path on the other side of the boundary between air and the glass.
So it's going to kind of bend as it moves through the glass.
And that's the refraction part of it. Good. So we want to keep those two terms in mind as we start to think about seismic waves traveling through Earth and what happens when they reach different boundaries.
Okay, reflection, refraction. Got it.
Good.
Okay, so here it looks like we're talking about reflection. And if we take a look at the picture, we got two kind of cartoons going on here. Okay, so we'll start with the one on the right.
Good.
We've got a truck and another truck all the way to the right. It's called a vibrator truck and a recording truck.
Yeah.
Now, the vibrator truck is sending waves probably through the ground. And we want to see how those waves travel through the ground. Now, we see when we get to some of these layers, they're bouncing off.
Right.
And changing directions. So some of them are bouncing right off a layer, and some of them are going through the layer and bouncing off the ones underneath. So that's going to be reflection, right? Okay.
That's going to be reflection. So the thing that students probably know this from is the movie Jurassic Park. In the beginning of the first movie, when they were looking for the dinosaur bones, they were out using the seismic generator to look inside the Earth for some difference in the material, and they were looking for bones versus the sediment that it was around. So in this case, they're looking for differences in the layers of the Earth based on where the reflections are occurring.
Cool.
Okay, and we've got another example here of the same kind of setup, just being towed by a boat, because we know the Earth's surface is covered about 3/4 by water.
Yeah.
So we need to know what's beneath the oceans as well as beneath the land.
Because we can't send a scuba diver down that deep. We learned from the Alvin sub.
So we have a ship that has the sensor towed behind it, and it's got a source to generate those sound waves and send that down into the water and then into the sediment or the rock beneath the ocean floor.
And then we can look at the different layers and how the waves bounce off those layers.
Right.
Okay.
Yep. So that's how we're figuring out where those layers are.
Okay.
So let's hang on to that idea as we think about looking deeper into the Earth.
Cool.
Okay.
Okay.
Looks like a little bit of math time, but really, you guys, this isn't tough.
No.
We're going to walk you through the basic idea of this. So just to get the basic idea of how this calculation is done. And I think the easy way to think about it is that if you send this seismic wave from the surface down into the Earth and it bounces or reflects off of a boundary,
Okay.
it has to go two ways. It has to go down and it has to come back up.
Okay.
Right?
So, okay, yeah.
So the distance from the surface to the boundary is really double.
Yeah, because you have to go from the beginning to the end, back to the beginning.
Yeah.
So your trip is twice as long.
Right.
Okay.
So that's why we're saying the distance times 2.
Okay.
So really we only want to know how deep it is. So we really only want to know one way.
We want that one distance,
we want that one way. And then what we really need to know is how long does it take for the wave to travel down and back up.
Okay.
And if we know what the material is, then because scientists have tested these materials in a lab, they know how fast specific types of seismic waves travel through that specific type of material.
So they can test the samples in the lab, and if they know what's beneath them already and see what the speed is, they can figure out what's beneath them.
Yeah.
Okay.
So that's the whole idea of using this equation and seismic reflection to figure out how deep those layers are.
Cool.
So let's look at one more example of this. All right, so if they want to figure out the thickness of the layer, they need the two-way travel time and the velocity of the material, and then they can figure out how thick that layer is.
Piece of cake. So if we know the material, we know that velocity from those lab tests, and we can just time how long it takes to bounce kind of to the bottom and back. Awesome.
Or we could time how long it takes from the occurrence of an earthquake to a seismic station someplace else on the surface.
Oh, cool, yeah.
So we can use that real earthquake data to get information about where the layers are in the Earth.
So we can set up like trucks and equipment to do this, or we can set up equipment to measure the Earth doing it naturally through the earthquakes.
Yep.
That's really cool.
And I guess we really do both.
Wow.
Yeah.
Neat.
Okay, so here's another example of the seismic reflection data being used. And you can see here's our little drawing of a source up there indicated by the S, so maybe an earthquake or maybe some source that is generated by humans. And the waves coming down and reflecting off of each of the layers and going back up and being received by that little box up there that's labeled R.
By the receiver, yeah.
Yeah.
And so we can see these different layers that come up based on the speeds that those waves travel through the layers and how much time it takes for it to get there.
Yeah.
Cool.
So the picture on the left is actually kind of a neat diagram. This is a diagram that shows the real record from a real seismic test. And this is the kind of things that geoscientists use when they go out and explore for things like oil or mineral deposits.
Yeah.
So they're looking for really fine changes in velocities of those seismic waves to identify where there's materials that are different densities.
So if they see changes in the velocities, they can see that there's different layers then down there. Okay.
Good, let's go on.
Okay, here's the big one.
Here's the big one.
Oh yeah.
You ready?
Yes.
So we're going to talk about shadow zones.
Okay, this was our big take-home message. We had to be able to explain shadow zones here today.
Exactly.
Okay, so let's look at the picture first of all.
Okay.
Right at the top of the Earth, it looks like we got some kind of source of energy, probably an earthquake.
Okay, so up there is the earthquake occurrence. Okay.
Okay, so radiating out from the earthquake, we've got waves coming different, being detected at different stations. Okay, but then I notice almost like a third of the way around, they stop. They kind of go right towards this outer mantle, and they stop right there.
So we've got the earthquake occurring. The earthquake energy leaves the earthquake in the form of P waves, S waves, Raleigh waves, love waves, surface waves, all different kinds of waves.
Okay.
In every direction, three-dimensionally, from that earthquake.
Yeah.
That energy goes out. Some of it comes straight down and hits the boundary between the mantle, which is shown in the brown, and the outer core, which is shown in the yellow.
Okay.
Some of that energy just stops there. So we know that this is liquid and we know that this is solid. What do we know about that wave then?
Yeah, because the P wave or the S wave was the shear, and it can't go through that liquid.
Because S goes through solid.
Yeah.
Right.
So if you see on the picture, these red ones, those must be S waves then, right?
Those are S waves.
Because they stop right at this boundary.
Exactly.
And the P waves go right through it.
Okay. So let's look at this S wave that just glances off of the boundary between the mantle and the outer core. This wave is following a curved path because of the change in density.
It's increasing in density, increasing in speed.
Until it gets to this boundary. Now, when it gets to this boundary, it's actually going back towards the surface.
Oh.
So it's going to start to slow down, right?
So it curves back up.
It's going to curve back up.
Gotcha.
And it's going to reach this point on the surface. Now, if we were to take a compass or something and measure around from where the earthquake happened over to here, we would find out that that is 103 degrees around the 360-degree circle of the Earth's surface.
And my guess is that on the other side, too, same thing's happening. You're going to be 103 degrees from the other side, so going the other direction.
Right.
Okay.
Now, we have to remember, too, that the Earth is a sphere, so this is really 103 degrees.
Like in three dimensions.
Way around in 3 dimensions,
oh
not
my gosh.
just two-dimensionally,
We
right?
can't show that in our videos yet.
No, that doesn't work.
Okay.
Okay. So we know that S waves that leave that earthquake, they could be seen anywhere along this arc from the earthquake all the way to the 103-degree point.
Okay.
Any seismic station could detect that S wave.
So if I was living right here, I could feel, or if I had a seismograph, I could feel the S wave.
It would record the S wave.
Okay.
Exactly. Anywhere between this 103 degrees, all the way around the bottom, essentially, the far side from the earthquake, back up to 103 degrees. No S waves are received in this region.
So you're telling me if I was at a station right here, at the bottom, kind of the opposite side of the Earth, I wouldn't feel any S waves.
Your seismic station would not even know there was an earthquake.
I would be so upset because somebody else has got S waves, I don't have them.
You'd be in the dark, in that
oh
shadow.
My gosh, in the shadow zone.
In the shadow zone. So the shadow zone for S waves starts 103 degrees away from the earthquake and continues around till you get back to 103 degrees.
Okay.
Okay?
And it's that three-dimensional thing, too. It's not just 2 points, it's like a whole bunch of points.
Right.
Okay.
So that's the S wave shadow zone.
Okay.
And what causes that S wave shadow zone is the fact that the S waves can't go through the liquid outer core.
Okay, because they hit that layer and they just stop. They can't go any further because they can't travel through that liquid.
Right.
Okay.
Okay, so that's S wave shadow zone. We still have to deal with P waves, right?
Oh my gosh, yeah.
Okay. So the P wave shadow zone.
Ooh. This one looks tougher because I'm looking over here and I see this first black one that's moving down, and this is a P wave. I know it's P wave because it's going through the liquid layer.
Right.
And it's starting to speed up because it's going closer to the surface.
Okay.
And then it refracts, it bends through another surface here. And I noticed that there's a big gap kind of over here between that 103 and...
About 143.
143?
Yeah.
Okay, so I got no waves over there. There's nothing in between.
That's correct.
So I think I know where this is going.
All right.
So
let's look at this one again. So this is a P wave, and it's following almost the same path that this S wave followed, right? When it reaches the boundary between the mantle and the outer core, it's going to continue to change velocity because it's now moving through this new material.
Mm-hmm.
When it reaches the boundary on the other side, it's going to change velocity again, and it's going to start to slow down because it's changing into a less dense material.
Okay.
Okay, so if we follow this path, we'll find out that from 103 to 143 degrees away from the earthquake.
Okay.
So you start at the earthquake, you measure around along the surface between 103 and 143. That's what we call the P and S wave shadow zone. No earthquake waves would be received at any seismic station there.
Oh my gosh, so nothing would be felt.
Nothing.
Wow.
Could be a 9.0 earthquake. If there's a seismic station in that area, they would not even register.
I would be really upset. And then if you were between this 143, it was? 143 degrees on each side, you would still feel a P wave.
Correct.
But only a P wave.
Only a P wave.
And no S wave.
Right.
And then between the 143 and the 103, you feel nothing.
Correct.
Wow. So we've got 3 seismographs right here. And one of them shows 2 little just kind of vibrations in there.
Yeah.
And we've got, because the P wave travels faster.
So it
it's
should
the
get
pH,
there
gets
first.
there first. So
Okay.
this has got to be the P wave. This is my S wave because it's slower.
All right.
So this one, where would that one be found? Because I got a P and an S wave. Oh.
So that's got to be between the earthquake itself,
Mm-hmm.
someplace around to 103 degrees.
Absolutely. So it's going to be closer towards the earthquake, in between that 0 and 103.
Second seismic station doesn't see the earthquake, the initial P or the initial S wave arrivals. So where's that earthquake?
That's got to
That
be.
seismic station. Sorry.
It's got to be in that P and S wave shadow zone. So
Yeah.
between that 103 and 143 degrees.
Yes, exactly.
Last one, it's just got one.
This one has just a P wave arrival.
Okay.
So it must be in the 143 to 143
Gotcha.
degree range.
Yeah. Cool.
Very good. All right. I think we're ready for a mastery check. What do you think?
Let's do this.
Let's go.
Okay. And what you guys are going to be doing? You're going to write a brief summary about how the S and P shadow zones are created on the Earth. Now, we want you guys to keep this really simple because this is for an 8th grader who doesn't know much about the Earth. So you're going to have to make sure you define certain things they might not know and maybe describe things that are a little bit easier for them to understand, right?
Yeah, so put in very simple terminology, your summary of how the PNS wave shadow zones are.
Keep it simple. Doesn't have to be too elaborate.
And a diagram is always really helpful, so I think probably drawing a picture is a good idea here.
Kids love pictures, and I feel like I'm a big kid. I love pictures.
Awesome.
Cool.
All right, good luck. See you tomorrow.